Welcome to our Compass seminar. It's a pleasure to present today's speaker, Pavel Berloff from Imperial College, London. It's the quick bio of Pavel. Pavel got his PhD from the Florida State. So he's, as a scientist, he's a native Floridian. So his PhD at least comes from this state. All right, then he worked as a research scientist at UCLA in Jim McWilliams group, and then he moved to Woods Hole as a scientist and senior scientist, right? And then finally he took this position at Imperial College London, right? And that took place in 2000.
10 years ago.
10 years ago, okay. 10-year anniversary at Imperial College. So Pavel research is in mesoscale dynamics and importance of mesoscales in large-scale circulation, in climate variability, in material transport, and overall dynamics of your system. So today we will talk about new approaches for parameterization of mesoscale eddies, which is a really difficult problem, but that smart people like Pavel can deal with it. The stage is yours. So.
Thank you, Igor, for the introduction. So as Igor explained to you, I like to skip over places, and also I do my science not deeply. So I skip from problem to problem, just touch the surface. Okay, so this talk is, well, you can see the title. There are some collaborators involved in some parts of the talk, a small fraction of the talk. Mostly it's my work for the last number of years. And the talk is in the overview style. So I will overview several different problems and different studies. So I will not go deep in technical details, but I will try to explain the big picture and talk about things which are even on the verge of being a little bit philosophical. And by the end of the talk, I will move to more difficult, basically more algorithmic things, but not too algorithmic. So that's my goal for now. And please feel free to ask questions. It's like a home audience, right? Okay, so just pretty quick words about the motivation, because you're all specialists in this. So the motivation is to parameterize mesoscale oceanic eddies, and I will focus on regions such as corrosion of the Gulf Stream, basically eastward jet extensions of the western boundary currents. So specific parts of the ocean. We all know that mesoscale eddies have profound kinematical and dynamical effects on the large-scale circulation, meaning that they transport stuff and also alter the large-scale dynamics. So either we resolve the eddies by brute force computing, and this is not going to happen soon, okay? Not in the foreseeable future, or we have to deal with them indirectly by eddy parameterizations, which is our jargon basically for turbulence modeling, different things. So parameterization is not just a simple isolated theoretical study, it's a work program. It's a very big field, and we just started to scratch the surface, I would say. Okay. So there are examples of good and working eddy parameterizations. So I'm giving here two examples, which is famous Jen McWilliams, which is basically downgrading diffusion of flare thickness, or eddy viscosity, which is downgrading diffusion of momentum in the turbulence. So when I say that there are successful parameterizations like this, what I mean is that for some processes, somewhere, with some very general degree of accuracy, overall, things like this can work. Okay? By no means we have a unified theory of turbulent eddy diffusion. We don't have anything even close to universal parameterization in terms of eddy diffusion. So we just have successful examples of something. And the level of success is usually quite simplistic, quite general. We put parameterization in and we say, okay, it looks like solutions kind of improved in both models. And this is it. That's the level where we live. Okay? So how come we're doing so badly with diffusive parameterizations? Okay? So the diffusive parameterizations, the idea of turbulent diffusion is actually this year will be 110 years old. if we go back to the original Jeffrey Taylor's paper of 1910. Okay? So more than a century of research. It's like, if you work on NSF project for 100 years and don't deliver anything significant, right? Isn't the time, to take account for that? Well, at least to raise the question, what were you doing for the century? So it's a good time, to raise question about us, like what have we done for a century? So that at the end, we have just isolated examples of something working crudely. Okay? And even more, the situation is even worse, because for the last 10, 20 years, and increasingly more so, people talk about moving away from diffusive parameterizations completely and exploring some other research lines. So what's wrong with the diffusion, and what are the other options? Okay. So the next slide is about diffusion. So I think on one page, I hope I will try to outline what's the essence of diffusion parameterizations and what are the main problems with it. So the diffusion parameterization, again, I know that we're all specialists, so I'm skipping many things and want to talk about main stuff. Diffusive parameterizations appear when you can replace eddy fluxes of something, so Q here can be anything, with flux gradient closure. So that's the formula which is around for, since basically Taylor's work. Okay, so we were taught this formula in graduate school. Our fathers and grandfathers were taught this formula. I have to tell you that this is probably one of the most mysterious formulas in science. Okay? So this is not a law, physical law. This is a dream. Okay? And even more, this is a very foggy dream. It's like, when in a dream you see something, but you can't see the details. So this dream is foggy because we don't know what are the primes here, we don't know what the bar is, we don't know what this K is. Okay? So half of the information there we just cannot discern. Okay? And still we believe in this dream. And sometimes this dream comes true, okay? So the dreams come true sometimes, like Jack McWilliams or Eddy viscosity. So what else should I say over here? Well, if this dream comes through, then we can replace turbulent stresses with something extremely simple, and we basically close the problem. And we can work only with the large-scale fields, and this is it, we're in business. The problem is solved. So what are the main problems? So how come it took 100 years and we moved basically nowhere with eddy diffusion? I put here a list of 6, as I think, main hurdles that we still have to jump over in this research. So let me go through them one by one. First one is the coarse-grained problem. Basically, we don't know how to define eddies and how to define large scales. This is all problem specific, and there are still lots of question marks. To put it simple, we don't know what the bar is, we don't know what the primes are. Okay? Sometimes we can fit a specific purpose, but nothing general. That's one big problem. Okay? So the second problem is the following. If we resolve this one, if we know how to coarse grain, if we know the fluxes, and we want to fit this magic K over here, okay? And that's eddy diffusivity. How do we fit it? How can we estimate it in principle? Okay? And there is a fitting problem. And the fitting problem is very, very difficult because in general, this object over here is not a scalar, it's a tensor. It's inhomogeneous, so it varies in space. It's anisotropic, it's non-stationary, it's full, okay? And we're always data constrained. So we can't map this object out. And even worse, the information that we have is usually Lagrangian information. So we basically have trajectories of floats and drifters. Okay? Lagrangian information is different from information from a point. So to put it straight, this is an unresolvable problem. This information is so non-local that we don't know how to fit it into Eulerian fields. So the next problem is the euploseness problem. Well, there are different ways of euploseness, but let's assume that this K comes out negative. Right? If it's negative, this is a negative diffusion operator, and we know that negative diffusion blows up in the final time. So it's an ill-posed problem. What do we do about that? Okay, the next problem on the list is degeneracy problem. What I mean here, and let me give you again an example of degeneracy. What if you fit flux gradient relation but there is a flux and there is no gradient. Gradient is 0. Basically, you don't have information to fill the gap. You can't estimate k at a point. Just insufficient information. What do we do about this? That's an open question. The next open question, and you know, not only physical oceanographers, but in general, people dealing with turbulence, they're shy even to talk about this. Okay? And the issue is that we don't know whether this subject K is unique and physical. Okay? If it depends on the gradient of the quantity that you consider, if it depends on basically grad of Q bar, like let's say tracer dependent, then it doesn't exist in reality. It exists for each specific tracer, for each problem. When I talk to people, well, we kind of know that it's not unique. So there are examples of this. But there is a conspiracy in the field. People refuse to talk about this. Because if we start talking about this, we open the whole box of questions like, what are we doing? And what were we doing for the 100 years? Okay? It will look like a dead end, or we have to overhaul everything. Okay? And finally, if we pass these 5 hurdles, the 6th one is the highest and the most difficult. If we know which parameterization to use, we still have to make a model for this scale, to put it in, to relate it to large-scale fields and constrain it with physical laws. Okay? So, well, I don't know what's your take on this, but for many people this looks probably hopeless. Okay? And still we're starting through. So, I want to focus on eddy large-scale interactions in eastward jet extensions of western boundary currents. So this is a notoriously difficult region to parameterize. All of these problems are there. Okay? So I'm focusing on this, and all these problems are there. So the question that appears is, what are the alternatives? We can keep going through this and struggle through, but are there alternatives? So the next slide I think I can skip this slide for you. So what I'm showing is just Roche extension. We all know that there is a jet meanders. There are lots of eddies, all eddies are multi-scale. The jet interacts with eddies both ways. That's a complicated region, and we have to parameterize eddies over there. Okay.
And then first comment, go back to the previous slide.
Previous? Yeah, sure.
I mean, we can talk more about this later, but
yeah.
You know, a lot of these problems are general. Not everyone's working on geophysical turbulence. A lot of these things you're talking about apply also to general turbulence.
Exactly. I would say all 6 are general.
But people develop turbulence parameterizations, and they're not perfect, but they're generally better than, say, the worst parameters.
I think you came a few minutes late, because on the slide before I said that sometimes, dreams come true. And we have successful examples.
Yeah, I mean, I guess there's the broader turbulence team where they develop these schemes, and sometimes they work better, fit data better than simple schemes. So are you saying, I guess you made a statement about something, every case seems case specific. And I guess
we still deal with cases. We don't have unified,
that's what I mean.
universal understanding.
That's understandable, right? Every situation is case specific. If you make a parameterization that fits the results better, then that's progress.
Well, did I sound too hopeless for you?
Yes.
This point? Okay, so I'm not hopeless. I'm still working on, with Igor, for example, on the diffusive closures and parameterizations. I'm trying to provoke a bit, just to show that. Yeah, because people usually picture this, with very colorful. Like, we're doing lots of progress. We're almost there. Almost done, give us more money, and this is it. That's not the case. 100 years of research, and there is a long way. That was my point. Okay, so what are the alternatives? Again, on this slide, I want to go quickly and just mention them. So one of them is to do stochastic eddy parameterizations. So forget about this flux gradient relation. Let's put something stochastic on the right-hand side. It's justified because we know that the turbulence is very random, very complicated, very multi-scale, and so on and so on. Okay, well, that's a rapidly growing field, I would say, not only in ocean dynamics, but in general in fluid turbulence. And there are several caveats. So I want to put them briefly over here. The first one, and I think by far the biggest one, is it has to do with temptations. It's very easy to construct something stochastic, put it on the model, and then start exploring the effects, publish papers, creating pictures. Always, if you do something with the model, the solution will be different. Sometimes it can look better, sometimes worse. I think this is a real distraction from science. Okay, so the real science has to be not about doing this, but about constraining all possible stochastic parameterizations, throwing out stuff which is bad. We have to have negative tests. And for this we need physical understanding and dynamical constraints. And out of million stochastic terms we have to find the single one which is well constrained and makes sense. So search for constraints, and finally a bad thing of this field, because it's so young, that people don't have general agreement on benchmarks and quality tests. Basically you can show, well, look, that's the spectrum I want, that's a spectrum without parameterization, here's a spectrum with parameterization. Something became better, okay? But well, that's not very deep. We have to develop, a metrics, skill tests, benchmark tests, and so on and so on. It's not there yet, okay, in this field. What other stuff? Okay, I'll go quickly. Alternative rheologies. So basically, instead of gradient on the right-hand side of flux, gradient has something more complicated. To put negative viscosity, for example, balance it by here viscosity on a larger scale, put negative on a smaller scale, or negative for short time. There are ideas of super parameterizations. Well, again, it's a broad set of ideas. For example, when you resolve things better in a subdomain somewhere, or you put an intermediate complexity model somewhere and solve it. To check like heavy-duty stuff over here. And finally, there is idea to make a blended approach of stochastic with diffusion, to make the K coefficient, the eddy diffusivity tensor stochastic itself. So this would be like a mix of two things. Within my talk, I will discuss several ideas eventually for parameterization. Most of them will be within the stochastic parameterization setup. One of them will be deterministic. It's a big field. So now let me consider, now let me be more specific. Okay, so that was an introduction so far. Now I'm becoming more specific about what I'm doing. So I want to focus on one well-respected, simple, idealized ocean model, which is double gyre ocean model. Stay within quasigeostrophic approximation for simplicity. So what is this? It's a square basin, let's say, of the size of North Atlantic or North Pacific, wind-driven. There are several isopycnal layers, equations for two layers. I have more than two, of course. Right here, so there is a material derivative. I solve with respect to potential reticity anomalies on the beta plane. There is, of course, some viscosity, finite viscosity, so there is a finite Reynolds number. Local friction, wind stress, it's more or less standard model. Potential reticities are related to stream functions give velocities, and we can affect all this stuff. Okay? So nothing sophisticated. So we know that in this problem, the eddy effects are important, especially around the eastward jet. How do we see this? So first, let's take a non-eddy-resolving or eddy-permitting, depending on your terminology that you like, model, which is 1/4 degree. So 1/4 degree, as far as I understand, it's a new standard for climate type ocean models. Are we there already? Are we still at half degree resolution with climate models with oceanic components? It depends. Well, anyway, so for climate kind of modeling, 1/4 degree is like really good ocean. So well-resolved ocean. Well, it's actually in terms of the mesoscale, it's not well-resolved at all. So it behaves really bad. Okay? So what I'm showing here is just a snapshot of upper layer stream function. That's the time mean of the stream function. What we have are subtropical gyre, subpolar gyre. The eastward jet is not developed because the eddies are not resolved. So this is really bad solution. Okay, so I'm going to use it as a straw man. What would be a good solution? The good solution would be to refine the mesh until the eddies are resolved, and the eddies start to do something. The solution changes profoundly. So for my talk, for the purpose of my talk, I want to develop an eddy parameterization such that if I put this miserably failed 1/4 degree model, it will improve substantially in terms of the eastward jet extension. That's my simple limited goal, to do something around this. Now I want to show you the same solution, but provided that the grid resolution is good enough. Just an animation. So, and that was stream function with contour lines and this potential reticity anomaly with color. So this is subtropical gyre, subpolar gyre. So if you don't like potential distance anomalies, well, just invert them and obtain stream function. Anyway, so the essence of the solution will be the same. So there are two western boundary currents that merge, that separate, and there is the eastward jet. So recall that on the previous, the Strawman solution, there was nothing like this in the solution. Because the eddies are not developed, and the eastward jet extension is maintained by the eddies. Okay? So it's a fundamentally eddy-driven feature of the motion. So any questions about this? So what I'm showing is just the upper layer, many other layers below. The resolution is, if I believe correctly, 7 kilometers for this animation. We go up to 1.
How's the time mean of that so different from the snapshot you showed?
Well, come on, look. Well, you always see this jet.
Yeah.
Just time in it.
Is it more narrow? Is it narrower, the jet?
Well, on the previous slide, the jet just not there. It's as wide as probably half of the base.
Okay.
There are two. Okay, let me show you what there. Just time in it with your eyes. That's easy.
I can time mean that with my eyes. Like so.
Well, yeah.
So
Look
you're saying
at this.
it's just diffuse, right? It's like constant velocity across. It's a very broad jet, I guess.
Well, look, that's the eastward jet extension. It's that broad. It's half basin broad.
Contours are about the same width apart the whole way.
Yeah. Or you can say that there is a jet, but it's so short over there that that's it.
Okay.
So I'm talking about a really big difference between 1/4 degree and proper eddy-resolving solution. So there is a feature that I want to obtain as a result of parameterization. Okay, simple to say, difficult to do. Let's move on. So we know that this jet is due to the eddies, but what's the mechanism? How do the eddies do this jet? Okay, just one slide on this and one animation. So one of the ways to talk about eddy effects is in terms of eddy forcing. So what is eddy forcing? I decompose the flow in bars and primes, for example, by spatial filtering, or I can do aliens. Decomposition in the timing and fluctuations. There are different ways. I told you already that the coarse-grained problem is not solved in general. Okay? It's not constrained. It should just fit the purpose. So if I decompose the flow, the advection curve will fall in 4 different components, 3 of which contain eddies, which are primes. So divergence of this is basically nonlinear effect of the eddies encapsulated in one field, which is space-time dependent. I call it eddy forcing. So the eddy forcing can be diagnosed. It can be also split in the timing part and fluctuation part. Okay. At this point, let me stop and show you how this object looks like, and then I will continue with the rest of my slide. I have only 2 animations in this talk. So what I'm showing is the eddy forcing for the first simulation. So first I showed you just the field, dynamical field, and that's the eddy forcing. So this eddy forcing is also standardized in the sense that it's normalized by standard deviation. Okay? Therefore, you see that its amplitude is kind of uniform across the basin. So without this, most of the amplitude is concentrated over here, but I'll show more pictures of it. So this is a very complicated object. So the way to think about this object is that this is a missing information from the eddies that affect the large scale. So the first idea that can come in mind, okay, maybe we can construct stochastic noise like this, put it in the non-eddy-resolving model, and we'll be all right. Well, yeah, that's one of the options, but there are many other options, and there are many problems. So I'll talk about it later. So what else can we say? Well, with your eye, you can see that this is not a random field; it's space-time coordinated. So you do see patterns. Any questions? Okay.
Can I
Yeah. Sure, but am I first?
No, go ahead. Of course, we go.
My question is kind of silly. Why do we have this kind of quiet zone in the southeastern corner?
Which zone?
Quiet.
Kind of quiet, dead zone.
This one?
Yeah.
Oh, well, there is a kind of Rossby wave radiating from the eastern boundary, and because my eddies are defined by filtering,
Right.
the wave is broad, so it's all on the large scale. So when you differentiate large scale field, you get small values. No eddies and large scale field is smooth. So the eddies develop as instabilities of this wave later on.
But we don't have the same feature in the north, in subpolar track.
Yeah, well, it's okay, all right. So this is standardized. So if I run a longer movie, this corner will be filled up at some point because the amplitude is 1 for every pixel over here. It just happens rarely. So most, yeah, but that's a detail. What's your question?
My question is, you're not considering space filtering, right? Just
Space filtering. No space filtering. So
Your
for this animation, it's space filtering.
Oh, space, okay.
Space
Bar is
filtering.
not space filtering, not time filtering. Your bar is space filtering.
Well, we have both. Ideally, it should be both. This animation and a few slides after that, no time filtering. Okay, let me go back to my talk now. No more animations. Okay, now, first important point that I want to discuss. So what's the mechanism that provides feedback from the eddies to the large scale flow that spins up the jet? Okay. So I'm giving to you without proof, but actually I will show kind of proof on the slide after that, the next slide. So the statement is that if you look at the time-dependent part of the eddy force, basically fluctuations around its time mean, then these fluctuations are correlated in a positive sense with the large-scale flow. So basically your nonlinear forcing from the eddies correlated with the large-scale flow response. You make the large-scale flow stronger. I'll show this on the next slide. So this mechanism we refer to as the eddy backscatter. In general, when people say eddy backscatter, they mean that the energy goes from small scales to large scales, one way or another. So here I'm talking about a very specific route of this energy transfer. It's the energy transfer via positive correlations between something which is very, very randomly looking, okay, and the large scale anomaly that appears in the flow. A very important footnote is the following, that if I take the Reynolds decomposition is decomposition in fluctuations and time mean. If I do this, then there is no way to see correlations between my large scale, which is time mean, and this EF prime. Time mean is not time dependent, just by construction. There is no correlation between something which is constant and something which is purely time dependent without mean. So there is no way to even talk about backscatter unless you do clever decomposition that allows large scale flow to evolve. So Reynolds decomposition, forget about this. Okay? It's dangerous, don't even use for the purposes of the backscatter. Just by construction, it's not going to help. Okay? It can be completely misleading. Now, what do I mean by positive correlations? Okay, so here I have to step aside and also say that my philosophy is that when we talk about parameterization of the eddies or parameterization of the scales, we can use it as a terminology, but we have to think about parameterization of mechanisms. We have to understand which mechanism we parameterize. It would be better to say we parameterization for such and such eddy mechanism, okay? Not for the eddies. So here I want to show you and single out the mechanism, and then I will talk about parameterization of this specific mechanism. So the mechanism is the following, the eddy backscatter. So I'm going to use just one slide to explain it. So here I'm showing a random snapshot of the full flow. So think about my first animation that I showed, just a snapshot out there. So I take this flow, I decompose it in large scale. Something is wrong with this. I decompose it in large scale, and it is by spatial filtering in this case. Okay? So this large scale is a live field, so it's evolving in time. So the jet moves back and forth. Its strength changes, everything changes like an animated. The eddies can be also animated. It's also a complicated field living on the top. That's the eddy forcing for this snapshot. Okay? Now it's not standardized. In the animation I standardized it. Now it's just as it is. So you can see that most of the eddy forcing is concentrated in the region where I'm interested to do my parameterization. Okay? Now, this eddy forcing has the timing component. So that's the timing part, and that's the transient part. Look at this number. In order to use the same color scale, I had to multiply the time in by 50,000. So this means that there is basically no time in the distribution. It's so weak relative to fluctuations that we're talking about tiny fraction organized like this. Okay? And most of this are huge, enormous fluctuations around. So which one of them is more important? The first one, the time in, is positively correlated with the large scale. You can see it. You have like red anomalies on one side, on the red side, and blue anomalies on the blue side. What does it mean? Physically, it means that this time in eddy forcing will try to spin up the eastward jet. That's a positive correlation. You cannot see with your eye, unless you're a robot probably, that this field is also positively correlated. Okay? So in order to see this, we have to go in and just do the calculation. It means that on average, you have more red anomalies on one side and more blue anomalies on the other side. So this field is also positively correlated in a consistent way, always. So which one is more important? Okay? This here one has tiny amplitude, but well-seen correlations. This one has huge amplitude, but difficult to see correlations. It's easy to establish this statistically. So the covariance of this part, not just correlation, but correlation plus the amplitude itself, of this part is 10,000 times bigger. So this effect is 4 orders of magnitude bigger than this effect in terms of spinning up the jet. Okay? That's why we're in a position to say that the jet is driven by backscatter in the sense that it's driven by fluctuations. But in order to see this, we have to do this kind of analysis. Furthermore, and it's not on this slide, if I do this covariance with a slight time lag, just weak time lag correlating eddy forcing with a future response, a week later, there is one more order of magnitude. It becomes 10 to the 5, not 10 to the 5. So we're in the situation of backscatter. Backscatter has to be parameterized. That's the goal. That's how we have to think about this problem. So how do we do this parameterization? Okay, well, immediately we can think about 2 routes, direct route and indirect route. So direct route is to think about my second animation when I showed you the eddy forcing. Direct route is to construct a stochastic forcing like this. Of course, we don't want to have it with full complexity, but to simulate most important features and put it in a non-eddy-resolving mode. Indirect route is to construct stochastic forcing like this, but instead of putting it directly in the model, do something with this, figure out flow responses to this stochastic forcing, and put flow responses. Okay? 2 ways. Question. Do you have a question?
Yeah.
Sure.
You've dazzled us here with a 10 to the 5th with the time average. But have you done the spatial filter of your transient eddy forcing to the scales of the filter that's involved, which is really what you're...
Okay,
this
so
is really the problem we're trying to solve, right? Is that also 4 orders of magnitude?
So if I understand your question correctly, you're telling me that what I showed here is just one spatial filter. So what if I take smaller or broader, right?
No, I mean, what if you spatial filter the bottom panel to the scales of the upper panel in the middle here?
Filter this one?
No, next to the right there, yeah. If you
Filter
spatial
this.
filter that to the scales of the one above it, does it look like the time? Does it look like the time? Does the spatial smoothing of that look like the time?
Okay. So
And is it comparable, or is it still, or is it?
let me try to rephrase your question.
Yeah.
I have to understand it. So are you saying that you want me to smooth this out
Yeah.
and then calculate correlation?
Yeah, and then
It will be about the same. It will be about the same.
Still thousands of times bigger. You know?
Yeah.
Okay.
Because you don't move anomalies. If you have positive anomaly next to negative anomaly, okay?
Yeah.
And we're talking about correlation, so I'm talking about like big spatial correlation. If you do smoothing, you're not going to change correlation a lot.
It
Depends on the scale.
So you will change covariance. So the amplitude will be reduced. anyway, my question to you is that that's a legitimate question, but the effect is not going to be strong.
Yeah, I was thinking you're 10 to the 4th, 10 to the 5th. This is not quite a fair comparison, but it's dazzling. Yeah, 10 to the 5th.
It's more than ever, right? So maybe if I play around with smoothing, I will go from 10 to the 4th to 10 to the 3rd.
Yeah, okay.
Maybe there is one order of magnitude, but not more. I think it's
Still
probably a factor of 2 or something,
Okay.
based on my experiences.
All right.
Okay, so what am I going to do over here? So I will keep these two roots in mind, and let me move on. Now I'm going to the next part of my story. So now that's the meat. So everything before that was philosophy, statement of the problem, and physical mechanism. Okay? I think physical mechanism is important, very well. So I want to talk about 4 different ways to parameterize this problem. 4 different ways are basically orthogonal to each other. And probably my goal is to show to you that basically the scope for ideas is very, very big. So you will see. Okay, so I will go one through one, and then I'll see how much time I left. So the first idea, and each idea has its ups and downs. So I will be honest about this. So the first idea, let me call it explicit stochastic forcing. Straightforward. So I want to construct a space-time correlated stochastic forcing, as in my second animation, and just put it on the non-eddy-resolving or eddy-permitting model. This is it. So how do we do this algorithmically? Well, so first the meaning of this, and the meaning I explained, that the stochastic forcing has to model the missing eddy forcing. It's the transient part. That's already explained. Second, how do we do space-time correlated noise? Well, there are algorithms. We can build in temporal correlations. We can build spatial correlations. We can do a lot of things. Okay? This is technical. What are well, does it work? Well, yes, it does, on the level that this kind of approach restores the eastward jet in general. It restores it as a big feature. Other caveats, what's the downside? The downside is the following. And actually, that's the route that I think most of eddy-stochastic parameterization people are facing nowadays, okay, and will face in the near future. When you construct stochastic noise like this, you put it on a coarse-grained model. So you hope that a coarse-grained model, basically on the scale which is close to its resolution, will digest the stochastic forcing in the right way, propagate the energy anomalies upscale, and basically it will work. We know from our experiences that in order to resolve S scale in the fluid dynamical model, we need probably 10 grid intervals. Okay? And even this is kind of conservative. I would say that if you have really sharp, really good schemes, that something on the scale of 10 grid intervals is resolved. Okay? So if your model is quarter degree, then what you resolve, which is 25 kilometers, that probably scales to 50 kilometers, I will represent. So this approach will always give inherent numerical errors close to the grid resolution. Okay? And that's a big problem. Not clear how to easily bypass it. So that's the first approach. So the second approach, which is kind of a heavy-duty, difficult approach, is aiming to overcome this last problem. So I will explain it step by step. So the goal is to overcome this curse of coarse-grained numerics handling stochastic noise and propagating it through. So the idea is the following. So first we can prepare space-time correlated stochastic forcing. First step is the same. Then, given a stochastic forcing field, let's bin it. So you've seen my second animation with a complicated field. Let's bin it, let's say 100 by 100 bits, for example, and consider each bin of stochastic forcing separate. We can do the following. We can ask the following question. What does this bin of stochastic forcing do to the large scale flow? What does this elementary stochastic forcing do to the large scale flow? one way to address this is to take the stochastic forcing, to take the underlying flow, and we know what the flow is in the beam. Suppose our coarse-grained model running through and crunching numbers, it will tell us what's the average velocity in this beam. So let's take this velocity, let's take its vertical profile. Let's assume that it is horizontally uniform. Okay? So I'm extracting flow information from coarse-grained model, treat it as spatially uniform, but vertically structured, basically as a velocity profile, put over stochastic forcing, and solve an intermediate complexity model. What's the intermediate complexity model? It's the model with infinitely fine resolution. I'm talking about spectral resolution. So basically we solve this response to local stochastic forcing exactly with computer accuracy. Okay, no error at all. What we have as the outcome, we can call it dynamical footprint. So instead of stochastic forcing, we have flow response to the stochastic forcing in some average sense, how the flow changed locally. Okay? What can we do then? This is a little bit crazy idea, but bear with me. We can take all possible flows that can exist, all possible profiles. For each vertical velocity profile, solve for the dynamical footprint. So we're talking about thousands, maybe million different dynamical footprints for all possible flows, and store this up. So we have exact solutions of the dynamical footprints stored in the lookup dictionary. Okay? Now, when the coarse-grained model, non-eddy-resolving model, goes through, it doesn't solve this million of different problems every time. It just interacts with the lookup dictionary. And there are machine learning methods that can do this very efficiently. Basically, yes, you solve one supermassive problem, but you do it only once. And then the model runs each bin every so often, talks to the lookup dictionary, picks up the right dynamical footprint, and upgrades itself. Okay? So this is conceptually difficult. In terms of the engineering, it's doable, and it's working. However, what I've done in this case, I replaced one problem, the coarse-grainedness curse of the first approach, with another problem. Yes, I don't have a resolution issue anymore because I solved for dynamical footprints without error density, exactly. But I introduced idealization in my flow. I'm dealing with idealization at the intermediate complexity level. I'm saying, well, I'm taking my flow, but I'm not using the full flow. I'm just pretending that the local flow is uniform. So there is this trade-off. But it's interesting that this approach can be organized, formulated, algorithmically coded, and it works. It restores the eastward. You have questions?
Yes.
Yes, please.
How do you make sure that the intermediate complexity model is what you want, is representing nature? If it has biases, then you'd be creating a surrogate for that model.
Okay, good. Okay, I understand the question. So let me explain. So we tried several different options, different levels of idealization, from more simple to more complicated. So there is a room for this. That's number one. Second, we always have truth. I have truth solution, which is eddy-resolving. I can always estimate the skill of parameterization against the truth. And at some point, I will show you how the skills are estimated.
So the truth is not in the modeling B.
Well, the truth is my first animation that I showed, in a coarse-grained sense. So first animation, but let's say smooth or coarse-grained. It has eastward jet now, right? So my truth is the eastward jet in the coarse-grained sense. So I know how to judge skills of my parameterization. Okay, so I'm quantitative about this, and I will show that. Yes.
When you say space-time correlated stochastic forcing, so stochastic is random, space-time correlated means it's not white noise. It's like little blobs of vorticity. Is that essentially what it's like, or?
Well, so temporal correlation is a continuity in the field. So when you look at my second animation, you see continuity in the field.
Right.
They don't blink. Okay, and spatial correlation means that there is a continuity in space.
Right.
You can differentiate the field spatially. There are patterns.
But when you say space, you have to define the space in that time.
Yeah.
You're choosing.
To build it, right?
It's a blob, right? I'm guessing, and it's
Well-
a finite time or infinite time.
So you're asking how this space-time correlated forcing looks like?
Yeah, like if you made a plot, it would be.
Well, okay, so I have to say that there are infinitely many levels of doing this. And you should stop at the level that you think is reasonable. Okay? If, for example, you build in your space-time correlated noise generator, let's say Gaussian correlation, then you will see blobs, something like this. But you can do more than that. You can build in anything that you want, any kind of space-time correlated.
What's your guidance? I mean, is it the
Data. We have to be guided by the data so far.
Okay.
We can do some physics, but on a very simple level. We know that mesoscales are correlated on basically Rossby deformation radius, and this is it. So when you do this, that's physics. But beyond that, and what else can you do? That's a big problem. Okay, so 2 frameworks, 2 more. So the third one, and this is where I have collaborators, a team working on this. For us, it's a big project, multi-year project. We're in the middle of it at the moment. So the idea is the following: it's completely data-driven. So forget about physics. Okay, data-driven. So suppose we have enough observations, enough missions about eddies from satellites, you name it, whatever. Okay. The idea is the following. So first we have to learn how to emulate the eddy field. Okay? By emulation, I mean pure statistical modeling. Okay? No dynamics at all. And there are ways now to build emulators. It's a big field. I don't know how it's here in the UK. Everyone talks about machine learning, artificial intelligence, all this stuff, and so on and so on. So students come, that's a hot topic. What does it mean over here? It means that there are lots of different ways to do statistical modeling of very complicated objects. From multilayer nonlinear regression to neural networks, lots of stuff. Okay, some of them are really bad, some of them are good. So first we learn how to emulate eddies. Emulate in some sense, in compressed sense, for example, based on the observed empirical orthogonal functions. Because we want to reduce the number of degrees of freedom. It's easier to emulate hundreds of patterns than millions of grid points. Okay? Then, that's the first idea. Second idea is to take emulated eddy fields and feed them to the eddy forcing operator. So remember this divergence of the eddy fluxes that I showed. So the primes will come from emulators, and the bars, large scales, will be solution of the non-eddy-resolving or eddy-permitting model. So the eddy forcing operator will just couple them. And this eddy forcing will be imposed on the model. That's our dream, okay? And this can be viewed as a dynamical constraint. It's a fundamental dynamical constraint because we know what that direction operator is. Yeah.
Why not emulate the eddy forcing itself?
Well, so the eddy forcing has a lot more degrees of freedom to emulate. And second, if you emulate eddy forcing, then your emulator is disconnected from the large scale. The large scale is part of the solution. So basically, your large scale has nothing to say about the emulator. So large scale will not influence emulated eddy forcing. So if we do it this way, then the eddy forcing is a hybrid. So half of it comes from emulator, half of it is dictated by the large scale flow, because large scale flow is the solution. So basically we couple solution with the external information. The way you are saying will be completely uncoupled. We do this as well, but there will be no coupling between large scale and eddy forcing.
But eddy forcing does not depend on the mean state explicitly.
Well, now it depends. So here in our philosophy it depends. So it should be calculated interactively. The large scale is part of the solution. So it naturally, eddy forcing also becomes part of the solution. It's just half emulated.
You're saying the eddy forcing operator depends on the state.
Exactly. So eddy forcing operator contains primes and bars. So in this case, primes are emulated and bars are the solution.
So,
It's not just
so if you think of the kinetic energy spectrum or something, you are cutting through the. Where is your cutoff? Is it outside? You are emulating the whole process, or you're cutting through the process. That's why. There's usually a cutoff process in larger simulations.
So in practice, we emulate now about 1,000 of EOFs.
No. I mean, in terms of what is it that you are doing? You are doing all the eddies, or you're doing part of the
Part of the eddies.
Part of the
Part of the eddies. So let's say a full eddy field would be million EOFs, and we emulate 1,000. I don't have animations here, but if I show you eddies extracted from the solution and eddies emulated, you will not be able to tell which is which. So there will be nothing in this animation which will tell you what is what. That's the level of similarity that we're working with. There is always a question, so what if this works, how much can we simplify? Can we go from 1,000 to 100?
How much you can? Because usually, like in a larger simulation, people aim for, let's say, a factor of 8 or 10 in each direction, 8 times 8 times 8 times 8 for the time, so 1,000 times cutoff from compute time, or something like that. So you cannot put it's the realistic number, okay? If you have multiple processes, you have multiple, the ocean has multiple. Yeah. So right now you have two processes. You have the large-scale gyre field and the baroclinic eddies. That's two. Some people say one. Ocean has gazillions of processes that are sometimes force different. Okay, so they don't necessarily depend on each other sometimes. Yeah, it's down the line. I mean, that's the
exactly. So our take on this, when we estimate skills of parameterization, we have like several benchmarks to let's say like 99% recover, to 90% recover, and to 2/3. So 2/3 are like low cutoff. If parameterization doesn't recover 2/3 of what we aim, we're saying, okay, well, this is it. We can't go below. But this is very empirical, right? If your goal is to recover, I don't know, maybe 50% of the solution in some metrics, maybe you need 50 or 100 UFs, and this is it, and this will be.
But you are trying to save off computer time or gain understanding, because computer time is nowadays cheap.
Well, emulators are cheap, so this part has no cost.
I mean, what would be great is understanding. I mean, you start with that. Because that's where the value is, because whether you wait 10 days versus 2 days versus 3 months, it almost doesn't matter nowadays. It's not the critical, unless you're making forecasts. The critical issue is understanding, because as you said, they've been waiting 100 years to understand better. And there are all kinds of simulations, high resolution, low resolution, middle resolution. People do not even look at this.
I completely agree with you. So for us, let me maybe explain to others. So this number, is it big or small? Well, from the emulating perspective, anything, that's fine. Emulators cost nothing, it's cheap. But we have to know, on the research level, we have to know how many degrees of freedom, statistical, we have to emulate, okay? Because for us, some people, Eddie Myers some time ago. So his dream was that we can parameterize with 3 degrees of freedom. Okay. Well, let me tell you, this is not going to happen. Okay. So all our numbers, even for very mild sort of skills, we're talking 100 and more, nothing less. So, hundreds of thousands. So forget about 3 degrees of freedom. Okay? But this will come out experimentally. There is another issue. You have lots of degrees of freedom, and you require certain depth of skills, let's say prediction skills in your emulators. The neural networks, like neural networks are in the air. People talk about neural networks. They're problematic. They can be structurally unstable. They will break down. This is actually a very dangerous game over here. Now people talk about blends between neural networks and some ODEs and PDEs. Okay. But overall, the standard is very low. People just simulate something, show for the first 5 days of emulation, and that just basically don't say that, after 5 days it blows up everything. Okay? Well, anyway, so I hope that in a year I come back and I will tell you more about this story. It's in the middle. We keep publishing and writing papers. So the last story, how much time do I have? Do I have 10 minutes or something to finish this up?
5 more minutes.
5 more minutes. Can I have 10 minutes? Sure. So okay. So the last one, and as I said, all 4 approaches are orthogonal to each other. Okay. So the last one, the main motivation was to do something do something as simple as possible. Okay. So this is motivated by real people who run real GCMs, like in Southampton or in many places in the United States. If you come to them and tell them, well, you know what, let's do, for example, this. Okay. You know what they will tell. Okay, right? Just get lost. Give us something simple. Give us a magic button or magic number or magic parameterization. Okay. So I thought about this for a long time and then tried to develop something which is extremely simple and still working. So the idea is local eddy amplification. The idea is the following. So think about a coarse gridded model, which has to be eddy-permitting. Okay? So this approach is for eddy-permitting model. So the model has to resolve at least something. Okay? If it runs through, we can filter it in space interactively, filter out eddies and then amplify them. How do we do amplification and relaxation? Nothing can be simpler than that. Okay? So there are no special derivatives involved. Very simple. But can this like super simple, super crazy idea work? Okay. I will show this on the next slide very quickly. But the essence of this approach, and actually the reason why it works, because this algorithm will attempt to amplify eddies where and when suggested by the dynamics. Not via external stochastic information, but using information from the flow itself. So if the model tries to develop vortex, amplification will help this vortex. If it tries to develop a jet, amplification will help at that time and this place.
Why are we amplifying? Why are we amplifying?
We amplify everywhere.
No, why?
Why amplify? Because coarse-grained models basically underpredict everything. They're too diffusive. They smooth out everything. And part of this smoothing is smoothing the backscatter, smoothing the jet, and so on and so on. So now with this approach number 4, I want to be what's going on with this? With this approach 4, I want to be more specific and just show what we do with the skills of parameterizations. Okay? I will need a few minutes for this. So first of all, amplification is like this. So primes are extracted by filtering, and the primes are exponentially amplified by this. T is amplification time scale. So if it's positive, Q prime is damped. If it's negative, Q prime will be amplified. This is it. How does it work for the model? Now I'm showing solutions. This is stream function. So here, the same model, the same reference solution, or the fine grid, that's not a coarse grid, that's a true solution, in which the eddies are very weakly damped. So the damping time scale is about 2 years, extremely weakly damped. Run for 100 years, take the average. What's the difference from the truth? Well, a small anomaly that develops over here, which is different from the truth. The jet becomes weaker. Why does it become weaker? Because we damp eddies. When you damp the eddies, you damp eddy forcing. When you damp eddy forcing, you damp the backscatter. Okay? So if you go to time scales, half a year or back to 10 days, the eastward jet can be wiped out completely. You kill the eddies kill the eddy forcing, the jet dies out because it's eddy driven. Okay, so there is a control of the backscatter. So the good news, and this is when I decided to develop this parameterization, is that it can be pushed the other way around. So instead of damping backscatter, we can amplify the backscatter. So that's the idea. Take the bad model and amplify the backscatter. So that's a weak amplification. So the jet becomes stronger. Okay. Very simplistic treatment. I'm saying that, well, this parameter T is uniform. So there is only one parameter to tune. What happens? Okay. Now, let's move to parameterization. I think this is important because I'm trying to show how skills of parameterizations, I hope, should be assessed. So first of all, if we parameterize something, we put parameterization in a bad model. Bad model can be bad model for 3 reasons. Usually all 3 reasons come together. Reason number 1, the model just nominally doesn't resolve anything beyond its grid scale. So it's blind to scales short of a grid scale. That's badness number 1. Badness number 2 is that this model is usually more diffusive, more viscous for many reasons, from stability to regularity of the solution and so on. And the reason number 3 is that the bad model has bigger grid intervals, so there are numerical errors due to finite difference. So the problems first and second, basically blindness of the model and excessive damping, can be isolated and dealt separately. How do we do this? We take a fine grid model and remove all the scales beyond some threshold, forcefully remove them, and make the model completely blind to the scales, but the resolution is still good. Or we can take this model and excessively dampen it. Or we can do 2 things together. The third one, which is due to bad numerics, always come on the top of this 2. You can't isolate it, right? Because that's not possible. So we do this systematically. We blind the model, we excessively dampen it, we do everything, and check the skills of the parameterizations for each situation. How does it look like? That's 2 examples. So this is the reference flow, stream function in the upper layer. This is what we should have. This is model blinded to 30 kilometer scale. This is model blinded to 60 kilometer scale. The jet is progressively weaker, and these are errors. So these are errors that accumulate. Basically, difference between what we have here and the truth. Okay? So we want to wipe these errors out. And here I have parameterized solutions, 30-degree blinded, 30 kilometer blinded, 60 kilometer blinded. This is how much we recovered. And this is how much we couldn't recover. So roughly with your eye, you see that we recover something like 2/3 or 3/4, roughly. Okay? We can do this more formally, and this is my last slide. And then I go to conclusions. Let me explain what this is. So each row is a situation when the model is blinded to a certain level. Okay? Each color over here represents different damping rate. So for example, this green line is that the model was blinded to that level, and the model was also excessively damped. So this is error. Okay? This coordinate is error. So that's the level of the error. So we were using L1 norm. Basically, we're taking time in from parameterized solution, time in from unparameterized solution. This is very conservative norm. We punish us a lot. For example, if we recover the jet with the recirculation zones, but the jet axis is slightly shifted, we're punished. Okay? So I'm not trying to show that using good norm. I'm using bad norm here. Bad for us. Now, the x-axis is the only parameter that we have. It's the amplification timescale t, which is negative, but that's its magnitude. So I vary it, and my question is there a window in which this parameter will improve the solution a lot? So when the green line dips in, that's the improvement. I can rewrite this as a relative error. So the initial error is 1. Ideally, I want to have 0 level. So when each curve dips down, that's the improvement. So you can see they dip to about 1/3. What does it mean? That here we recover this bad norm about 2/3 of the eastward jet. So 2/3 of the time in eastward jet are recovered. Okay? And if we blind the model even further, so this 65 by 65 degrees, that's not a model. This is really dead model. It doesn't resolve anything. Even then, we can recover about 50% of the eastward jet, which is really remarkable, I would say. Okay? No other tuning. I didn't try to tune T as a special map, nothing. So this is as it is. Okay? And we do these kind of things also with the numerical error included. Okay? Not on the fine graded, blinded, and excessively damped, but going really to the bad model and so on and so on. So the bottom line is that even this super simplistic approach can recover more than 1/2 of the eastward jet. Okay? And summary of the results. So first, I discussed this eddy backscatter mechanism, and my point is that we should not parameterize eddies. We should parameterize eddy mechanisms. Okay? At least deep in heart. We can say that we parameterize eddies, but we have to mean that we parameterize mechanisms. We have to understand this mechanism first of all. Second, I discussed 4 different approaches which are completely orthogonal. Last one, for example, super simplistic and deterministic. The other 3 are stochastic, different complexities. Okay? I think my point was to show that the scope for parameterization is very, very broad. So there is a lot of room for theoreticians, for modelers, for everyone. Please come in. And finally, I showed that we have to estimate skills of parameterizations in a more systematic way. Not just showing, something that one figure is better than another one, but make it quantitative. Talk about numbers, quantitative assessments. And of course, there are lots of other extensions that we're facing. Thank you very much. Sorry for
Well, thank you very much. Maybe we have just a little bit of time for one quick question, and otherwise we can move the discussion to wet lab at 5 o'clock. So if you want to join us, we'll be there. But now maybe a quick question.
How long are you going to be in the web?
Until midnight. Oh, maybe an hour or so, maybe less. We'll see. So I have been invited to join us after around 5 o'clock or so. If you don't have a question, well then let's thank Pavel again.
Sorry for being over time.